Hello everyone. Today we are going to solve example 2.5, which is a classical feedback control problem. This question gives us a block diagram of a system with a variable gain in the forward path and a simple integrator setup. It's a unity feedback system, which means the output is fed directly back into the input to see how well it's following orders. Today we are trying to figure out the breaking point of this system. In control systems, usually, if you crank up the gain too high, the system stops being smooth and starts oscillating. Basically, it overshoots its target and has to bounce back. Thank you very much.
Okay, so the diagram we have here is a closed loop feedback system. And we have an input. The input refers to the signal, the desired signal we want to achieve from the system. So now the input is fed into the summing junction. And we have a feedback signal also coming into the summing junction. So after comparison, the difference becomes an error signal. Now this error signal is passed through a forward path transfer function, and then the processing becomes our output function. So now the output is fed back to the feedback path to the summing point to again undergo comparison. So now this helps to reduce error and increases stability in the system. So as you can see, our feedback path has no block, and that means it's a unity feedback. That means it has a feedback gain of 1. So now for our forward path transfer function, we have the gene here. This gene refers to the gain and is very useful in system response. Thank you.
To analyze this control system, we need to determine the closed loop transfer function. And from block diagram reduction, we know that the final transfer function will be this. So when we put in our values, where g of s is our forward path and then h of s is our feedback system, we get this substitution. And then when we simplify, we get this.
So from the previous step, the closed loop transfer function was obtained as this: g over s squared plus 3s plus g. So we identified the denominator because it gives the characteristic equation of the system. So the denominator here is s squared plus 3s plus g is equal to 0. Then to analyze further, we compared this equation with the standard second order characteristic equation, which is given by s squared plus 2 zeta omega ns plus omega n squared is equal to 0. Then comparing the coefficients of both equations, 2 zeta omega n is equal to 2. Then omega n squared is equal to g. Sorry, 2 zeta omega n is equal to 3, and omega n squared is equal to g.
Okay, so in control systems, the overshoot of a system is dependent on the damping ratio. If the damping ratio is greater than 1, we say the system is overdamped, and therefore there will be no oscillations. If it's equal to 1, the system is critically damped, and then if it's less than 1, the system is underdamped. So in the previous equation, we compared 120 to 3. So therefore, we are going to find the gain, and this is the equation given to us to find the gain. So we just substitute in the values and make the results, and we have gain to be equal to 6.25.
From the previous step, we established that the minimum value of G, the gain, needed in order for the system to exhibit overshoot is 6.25. And on the problem asks us to consider the situation whereby the gain is twice the minimum value. So to do this, we simply multiply our gain by 2 to get 12.5. So generally increasing the gain also increases the responsiveness of the system, but this may lead to greater oscillations in the output. Also, from our comparison with the standard second order equation, we established that the natural frequency is equal to the square root of the gain. And so now we have to find the natural frequency when the gain is doubled. To do this, you just find the square root of our new gain, which is 12.5. So finding the square root of 12.5 gives us 3.53 radians per second. So this is our natural frequency when the gain is doubled.
Okay, so we'll be able to find zeta, which is equal to 3 over 2 omega n, and that's going to help us to find our damping frequency. Yeah, so then the damping frequency equation is giving us the normal frequency, which is Wn, multiplied by the square root of 1 minus zeta. And so when you do the substitutions, you are going to get 3.197 rad per second.